Okay, so Dr. Hakim.
No more. No.
Thank you very much.
Put this here. Just a minute. Good morning. Can you hear me? Can you hear my morning voice? Of course, in this room, everybody can hear. Yeah. Well, I take this privilege to actually address you the first series of lecture, and it's of course a great honor for me. A very good morning for everybody. I hope you are in a very good shape. Yes, looks like you are all in good shape. Also, to all those in the Zoom, good morning. So my first talk will be in a very introduction part of what are we going actually to learn throughout this international virtual course. And I have a somewhat handicap. If I use my mask, then I will soon lose my breath. So if you don't mind, may I open my mask? Yeah, I think I contain no virus at all, because I have a very effective way to kill the virus with the smoke. Okay? So and then it turns out to be very effective, at least for me, not for you. So let's start. Yeah, the first talk will be an overview of astrophysical modeling and computation. And I should admit, this is not all of the materials originally come from me, but speaking roughly, I did my first modeling 40 years ago. So you were not born on that time, right? So it's a good time to tell lies to you, because none of you witnessing this. When I learned computer program using BASIC on that time. So the challenge is how to make a very good computational, and the challenge is how to model the stellar interior. So I have to solve 4 differential equations, very complicated, nonlinear, and I have only 8-bit computer, a very old HP PC at Bosca Observatory. So what did I do on that time? Well, I created the program using BASIC with many errors, and actually it was not a compiler but an interpreter. So every time you wrote wrongly a syntax, so it will stop in the middle. So you have to rerun again from the beginning. So after gaining this experience, what did I do? I took a mattress from my room and bring it to the computer room at Bosca Observatory and lay down there. So I ran the program and sleep. And when I heard a sound, a beep from the computer, there must be an error. Then I wake up, run again the program, and sleep again. So it took about 8 hours to finish 4 differential equations on that time using a very native BASIC. And thanks to the present technology, we are now having very different situation. But anyway, the basic philosophy of modeling and computation remains the same. So the key is how to actually solve scientific problem using our genuity. That means that the best is, of course, to develop our own method. And just like an astronomer who would like to build an instrument. So because there is no market, in the market we cannot find easily an instrument that can solve all of our scientific problems. So you have to create everything by yourself. That's the best to do. So that is the basic thing that I'd like to tell you in this very first series of lecture. And I hope you have some idea after hearing this. And of course, there will be a short assignment, very easy assignment, according to me. And of course, it should be also easy for you. So let me start through this. Oh, should I see here or there? Should I share this? Oh, you didn't tell me. Just a minute. So I have to share this. Okay, just a minute. Sorry for that. I thought everything is okay. Yeah. So this is the first course. For this is an overview of astrophysical modeling and computation. This should not cover all aspects of astronomical computation or astronomical modeling, but let me see the basic thing of this. First, when we talk about astronomical modeling and computation, there is a word computation there. And this computation actually thought by many astronomers to be a very important part. This is actually recorded in a very good book, a report from National Council, telling that how important astronomical computation now is in the pace of astronomical research. So astronomical computation becomes more and more vital in our research. This doesn't mean that you should turn away from the observation, because observation is the basic way to get the data, and eventually you have to, of course, solve any problem and match it to the data, because when we create a model, we have more or less a very wide spread of solution of any kind of model. Then you have to converge to one particular solution using the observational data. So that's what makes astrophysics so unique. Okay? So when we talk about this, the basic is still the same. So what we do is actually a computer experiment or numerical experiment. These are actually, in view of science, is a mathematical model for stimulating or for simulating the behavior of complex physical systems. So now, in the Department of Physics, we have a complex physics. So astronomy should also be one important part in the whole scale of a complex physics system. So there are many reasons of why computer experiments is now becoming more important and important. First, even for an instrumentalist who build astronomical instrumentation, they need to design. And when we design, we do computer work. See? So computation is a very indispensable step prior to cutting all the metals, assembling it, and making a telescope. So we have to at least make an optical design. And when we talk about optical design, is in the computer simulation optical design, you simulate the ray, of course, by particle, and inject it to the optical system and try to see the best focus or what is the property of optical things in the focal plane of any telescope. So to help design a complex device before using expensive technology to actually build this. When we speak about CCD, the sensor is a product of microelectronics, and it's very expensive because that's the heart of any camera. So before actually you embark into this, you need to design it carefully, properly. So that is the area where computer play an important role, even in material physics. So we see there is a very fast development in material physics, okay, because owing to this computational power and computational method that has been developed. And second is to gain information about physical systems that are not readily available in laboratory experiments. Okay? When we speak about forbidden line coming from a nebula in the interstellar medium, so that forbidden line cannot be produced in the Earth because we have a very high density of atmosphere around us. That can only happen if there is a radiative transition, a spontaneous transition, under the condition of very, very low density, almost vacuum. That can happen in the space. But of course, we cannot come there and measure. So we have to do some experiment. Of course, we can observe this spectroscopically, but how actually to synthesize this using a computer? That's a great challenge because we have to address many physical issues that has not been investigated before. Okay. So to gain information about physical systems that are not readily available, then astronomy is a very perfect example of this. There are many extreme phenomena in astronomy that inspire us to find or to invent a very good mechanical mechanism to explain this, to explain what is happening, and to help understand extremely complex system. And once again, astronomy is a very good example of this, a supernova, an unimaginable explosion at the space. So we always speak about atomic bomb in Hiroshima and Nagasaki. That is nothing compared to astronomical scale, nothing compared to even a prominence in the sun, or even a flare. So then, in the universe, we know that there are two parameters that never remain constant, position and age. Everything in the universe is moving. Everything in the universe is getting old. So, of course, it is proper to address the system is not a static one, but a dynamic system. So dynamic systems that evolve with time, such as galaxy, have 3 coordinates of position and also 3 coordinates of velocity. So since everything is moving in the space. But we can only see the projection, X and Y, and line of sight. Okay? So based on this, how we actually deproject and get an idea about 3-dimensional shape of the object that we'd like to see. That is a very important thing that astronomers address from time to time. Distance and the actual shape of the object that we are observing. So to determine the underlying structure of the universe, of course, this is absolutely necessary to use computer. So there are 2 actually systems that we can consider here. One is actually the static system, in which we take actually the snapshot of an astronomical object in one particular condition. And second is the dynamic. We see how it evolves, how it moves, how it changes as a function of time. So there are many situations in nature where we can view a physical system as a collection of particles. From the statistical physics, you have been taught that we can consider everything as particle and try to, of course, get some idea about the physical condition under one condition of a particle. It can be a degenerated particle, a normal particle, or a particle following the relativistics. Then we come to three basic statistical physics, like the distribution of Maxwell-Boltzmann, yes, Fermi, and Bose-Einstein. So this law of physics is actually also applied in astronomy by creating all the astronomical objects as a particle. Okay? Because universe is a very big ensemble, and it consists of galaxy. Galaxy also an ensemble of stars. Stars might be an ensemble of planet system. So there is a hierarchy of particle system that we can consider. And of course, this particle interacts and obey a certain laws. So once again, astronomy offers many excellent examples of this. The planet in the solar system, stars in the galaxy in the universe, in which all obeys the Newton law of gravitation. So this particle actually have various physical attributes, as I mentioned before: mass, velocity, position, and distribution, actually, eventually. And each particle interacts with all other under force of gravity. So this is known as a very famous topic in astronomy as an n-body problem. So of course, n-body problem can be reduced to be 2-body problem, or 3-body problem, like Earth, Moon, and Sun. And then if we go further, we actually add the sample to be, and we have this n-body problem. So where n is a number of particles used in computer experiments. Okay? So yeah, now the challenge is how to set up a numerical experiments every time you face this problem. Okay? The general step involved in running computer experiments can be described as follows. First is find a physical or observe physical phenomena. So the idea of science sometimes comes from observation, or we think about this. We have a Gedanken experiment, and then we try to, of course, figure out the most reasonable concept to explain this. So this comes hand in hand. So we choose the physical system that you wish to investigate. Some of you are interested in solar system, galaxy, okay, cosmology, or stellar systems. There are various topics in astronomy. You can select. Then you like to investigate. This idea should come up from you, okay? Because that actually represents your interest. So once you have an idea, and this is what's so-called after you formulate the problem, then you come to the selection of mathematical models. So what mathematical models actually can approximate the solution of this system, or can describe the behavior of the system that we are actually investigating or observing. Okay? So this generally uses some simplifying assumption to describe the working of the physical system. You cannot go into the complex system directly. You have to go step by step. Okay? You have to assume, you have to simplify, and then gradually you go up to the more complex situation. That actually represents why we have the sarjana and master and doctoral degree, because this is like a pyramid. You learn general astronomy in the bachelor degree, and then you get into a more narrow field in the master degree, and in particular in the doctor degree, you select one very typical problem and solve it using a high scientific method and sophisticated scientific methods. Okay? So once you have this mathematical model, remember mathematics is developed. Mathematical concept is developed under a very basic, basic view in which all the function is considered to be a continuous function. But when you change from this analytical, logical, to the computer, which is discrete, then of course the very normal way is we discretize the model. You actually transform this continuous function or differential equation into algebraic approximation, which computer can solve, because the computer has limitation, not us. We have infinite continuous mind, but the computer work in a discrete. Computer work with a bit of information. Okay? Computer mostly work, the processor mostly work with integer. So there is an interaction between human and computer in which you have to find a very good way to, of course, scale this concept of number into which will be processed by the computer and return the result to you and interpreted to you in a continuous way. Okay? So one must be careful at this step to introduce as few errors as possible. So that's why in astronomy, statement about error is very important. You cannot say just the distance. You cannot say just the metallicity, for example. But you also have to include the uncertainty. Imagine what happened when astronomers calculate an orbit of the comet back in 2002. And they thought the media that this comet will intersect the Earth. And everybody got so panicked because of this. But the astronomer on that time forgot to mention that the uncertainty is 200,000 kilometers or 2 million kilometers. So there is actually uncertainty. And no doomsdays, don't worry about that, because the comet didn't hit the Earth on that time. So both time and space must be discretized, in which produce, and because of the consequence of discretizing this, it will introduce a round-off error or cut-off error. Yes, that also follow all the result of the calculation. And then you find the algorithm. Algorithm is actually a description of the process, a step-by-step process. Computer is dumb. Who is clever? It's you. So you create all the receipt, and the computer will do it for you. Okay? So please think about computer is your assistant. It is not you, the slave of the computer, but the computer is a slave of us. Computer help us to solve the problem. And in order to make the computer works for us, we need to create or develop an algorithm. Okay? So choose the choice of discretization is often related to algorithm that we use. So that's why you go through the lecture of astronomical computation and numerical method for this. You need to be able to solve the discrete problem rapidly on your computer. So because the computer is assisting us to compute fastly, if it turns out that you work slowly, the computer is useless. Or you are useless. But you are not useless. You are not optimizing the computer for you. Okay? So think about this, because nowadays I see many students rely so much. They delay the report to me as a supervisor, and the scapegoat is always the computer. Then I say, please throw away your computer and come to me. And they never come. Okay? So they depend so much on the computer. That is not really correct, that attitude. So the last challenge is to create a computer program. I found these days it is hard to create a computer program, despite of very many computer language. In my time, the computer language is only basic, Fortran. Nobody knows Fortran, right? At least your age. And assembly, nobody even heard that. Okay? Assembly is a machine language. So writing the code is what it's all about. So because your result, your originality is described in the computer code, in which you're going to run the program, or you discuss the listing of the computer code with the supervisor. So the code needs to be well engineered to make use all the available computing power. When we speak about the computer language, first, the body of the computer language is start from declaration. We declare which one are variable, which are constant, what kind of variable, a double precision variable, single precision variable, a complex variable. Okay? So because the computer program actually teach us how to think systematically and structurally. Okay? So once you create a very structured program, it's easy for you to trace what is wrong in the program if it doesn't work properly. So be easy of use and easy to modify. That's the key. And don't forget to, of course, make a documentation in the program so that you can see the algorithm clearly from the program. So in my age, there are two kinds of programmer, a spaghetti programmer and structure programmer. I'm a spaghetti programmer. I write anything and I forgot to put all the document. So only me can see that. That's useless for readability. Okay? But the well-structured, they make a module for this and make a main program and access this. So that's why, thanks to all this structured programmer, the world now possessing a library of program. Think about the Python, you have so many library, and think how the library actually built. That was built mostly by structured-oriented programmer. That is everybody to use. And then, after you create the program, what are you going to do? Of course, you're going to make some experiment with the computer. Okay? You get to run your computer experiment, but you need to know what are you going to test. So not just running, yes, because sometimes we have to stop. Okay, it's running. Okay, I cannot see this. Yeah. And yes, let me see what else. And how to do analysis of the data during experiment, and pretty pictures are, of course, vital at this stage. So why I said pretty picture? Because the first analysis comes when we look at the result. And imagine, actually, what has come out from any computer experiment is a sequence of numbers. It's not easy to see that. So that's why that is time when you need a visualization tools. Okay, to display the result to you that ease you to make analysis. So that's why modeling and visualization comes hand to hand. You can run a computer experiment and then you have to present the result that ease you actually to see then make interpretation. So it was so expensive in my time because I have to use two computers. One is to display and the monitor specification is very different. And if I add image, I have to employ another terminal there. So think about me working with three computers. One is to process, and next displays to show the graphic, and the last is for display. But now everything is actually packed in one single laptop like this. So when we discretize the mathematical model, the idea will be like this. The major task when setting up computer experiment is making discretization of mathematical model. So discretizing a mathematical model. So this is a very good illustration showing you that the sine function come from the mathematical equation is actually a continuous function. But of course you cannot actually do it in a computer because in computer everything is represented by bit. So of course when you look at this, how can we create such a computer sample of data that represent very well the sine wave? So first, you need to have a very good function, and second, you have to sample all the points resembling this line closely. There are two solutions here. First is to put the interval as short as possible, or create a large number of dots here. And that costs a CPU time and memory. Okay. The number may cost, of course, the number of points will occupy a lot of memory storage, but the short interval will, of course, ask the computer to do processing many times. So you have to find the balance between this. Because actually you are not going to stuck into representing this, but you're going to solve physical problem. So every time you do computer experiment, please think that my dream is to solve physical problem, not to be the slave of the computer. Okay. So it can handle a set of discrete points that represent the continuous sine wave. Computer is very fast. You take advantage of this. So the computer can deal with these discrete bits of information, adding, multiplying, and storing, etc. That's the power of the computer that you have to make use of this. So while there are many systems in astronomy which can model using computer code, we will be concerned with dynamic simulations. Because dynamic simulation nowadays is very easy to be done. Which means that the study of systems that evolve with time and space, movement, and getting old. Okay, these are two examples in the universe. So we can also cover actually static simulation. We like to get a snapshot of the explosion of nova in one particular time. That means we are actually photographing this using a computer simulation and see what happened from one time to the other time. Of course, owing to the computer power, it's easy now to jump into dynamic simulation, but remember, everything must be done step by step. You have to understand static system first, and then go to the dynamic. Don't go directly to the dynamic. That is especially very dangerous if you don't know the underlying physics, the correct physics that underlying this system itself. In most astrophysical systems, the global properties of system are determined by force of gravity. So gravity is the key for this. And we should think that gravity is the only force that we should consider. They are electromagnetic, weak and strong, but that's of course negligible compared to gravity. Gravity plays a very important role. Well, there are also other forces involved like electrical and everything, but if we speak about gravity, that should be sufficient to consider most of the particle system that we like to consider. So there are examples in astronomy, dynamical systems in astronomy that are governed by gravity, that we can model using numerical simulation include solar system studies. I'll list some of the topics here that might interest you. Study of dynamic and stability of the solar system, evolution of planetary, asteroid especially, and the motion of interaction of asteroid in the asteroid belt, modeling planetary rings, and orbit of comets. I think Dr. Budi Dermawan will address this in the course of VJ. And the star system, I myself, my research is on this, but in binary. Yeah, because if we speak about star system, it starts from binary, triple system, association, clusters, and galaxy. So formation of stars through the collapse of giant molecular clouds. People now using supercomputer actually to simulate this. The dynamic of binary systems, small star cluster, and formation of evolution of globular cluster. These are some of the topics that can be covered. And if we go further, so galaxy studies involve dynamic of spiral galaxy. You see many pretty pictures showing you interaction between two galaxies that have been observed by Hubble Space Telescope. People try to simulate this. So people now trying to simulate also the tight force between one very compact stars, yes, which eating actually normal stars, or one compact black hole eating stars. Because people try to explain the black hole that has been observed recently with the Event Horizon Telescope. Interaction between galaxy and galaxy mergers, evolution of galaxy, galactic clusters, and cluster dynamics. I think this will be addressed by Iqbal, right? In this, yeah. So I rely on you. And then, of course, we go to the very mainstream now is the cosmological studies. So owing to the avalanche of the data, so many big data, these are coming from the surface and the James Webb Space Telescope. Cosmology has a boost, a strong boost, in which people are trying to, of course, to advance computational method in trying to explain the observational results coming from the most sophisticated telescope now, like formation of structure in the universe, dark matter problem, the area of Buhesti, and evolution of the universe. So throughout my course, I'll mention many names promoting our stuff. So whenever you're interested, come to those professors that I mentioned to you. There are just some of the systems that have been modeled. So over the past 2 decades, I mean really 2 and 3 decades, These are mostly using dynamic computer simulation. So when I speak about the structure and evolution of the star, which is now the course called stellar physics, the reason why we call it stellar structure and evolution, because in the past, I said in the 1970, even to solve a structure of the star, it needs computer time so much. And the dynamic comes to the stellar evolution, because stellar evolution is actually a model, a static model of the star, yes, of course, ordered in a sequence of time. There's a very good story of Professor Chandrasekhar when he has to solve the problem of the mass limit of white dwarf, 1.44 solar mass. So he employed 40 PhD students to calculate, to solve the Land-Emden equation in Princeton. And it took 1 week. And the result, it comes to the conclusion of 1.44 mass, because he must calculate a mass as a function of the degenerate core that time. So then he got a Nobel. But now I can do it less than 5 minutes with this computer now. But that was happened in 1930, 1940. So the idea is the same, but the way we do it is more efficient. So let's come to the mathematical model. Okay. So Bu Nuning is going to discuss about this later, but let me constrain this to mostly astronomical topics. There are two main parts of this dynamical code. First is the force calculation and time evolution. Okay. Both of these components can be described by mathematical models. And this means that we have a set of mathematical equations, not only one part mathematical equation. And when we speak about differential equation, not one differential equation, but a set of simultaneous or partial differential equation, or differential equation with a higher order. So when we speak numerically, you have to solve it recursively. Okay. This means that we have a set of mathematical equations to solve, which will tell us about the future state of our system given a set of initial condition. If you remember, when we solve a partial differential equation, it comes into two ways of solving this. First, put the boundary condition, or put the initial condition and run it. Okay? And you have to be very careful with the initial condition, because sometimes it runs divergent. So you have to, of course, guard this by introducing the tolerance, or a way where you can stop the computation. Otherwise, the computation will come, because the computer is dumb. You ask him to loop, he will do it for you for a week, or a month, or years. Okay? Once we have our mathematical model, we need to discretize and use numerical algorithm to solve the discrete system on a computer. So next is my personal experience, things to think about in astrophysics, for example. Only an incredibly small number of problems can be solved analytically. So this doesn't mean that I am discouraging analytic. But in the past, for example, when people solve the celestial mechanics, they always consider the body move around the central of mass in the circle shape. But what happened in the universe is not like that. It's an ellipse. So what people did when they have no computer, they basically introduced a circle function with some higher order terms, which is called the perturbation or disturbance. But that's not a realistic way in solving analytical problem, because in many astronomical problems, how to solve it, we cannot use an analytical way, mostly. Okay. Sometimes linearizing equation throws away the nonlinear behavior we want to study because of this. And second, in the old time, people tend to reduce the dimension. Okay? We cannot solve easily in 3 dimensions, and then we solve it in 2 dimensions because of limitation in mathematical, analytical way, and limitation of the computing power at that time. Think about the star. What is the basic shape of the star? Spherical. But when 2 stars come close together, okay, because of the tide force, so one of the stars will become disturbed, the shape. Okay? And the shape is no longer spherical, but it's not also an ellipse. It's not a triangle even. Don't think about triangle. It's actually only one part. The substellar point will be elongated, and the rest the averted side will be shape. How can you geometrically represent this in an analytical way? No, it's impossible. You need a computer for that. To realistically represent the actual shape of the star, and think about black hole. When it comes to the star will be very much elongated in one part, and the other still remain because of the tidal force. So, in the old time, it's impossible because we don't have computer. So what we do is to assume a spherical and also spherical and introduce some, of course, term that represent this elongated part. Very unrealistic, but it works in the old time. You can see it from a paper published in 1950 or 1940. So when they try to solve, for example, a very well-known astronomer, Professor Kopal, he was also my supervisor from Manchester. He produced a very good book called the Closed Binary System. And that book, starting from the first page until the last page, contains only mathematics. Have you ever read that, Pak Iqbal? I think Pak Ivan is the younger generation. You even never touched that book, I think. I used that book to sleep as my pillow because it's a very thick book. And when I look at this, I soon become sleepy, okay? Because so many beautiful mathematical equations at that time. So he speaks about mostly introducing harmonic function to represent the actual shape of the star. We have Roche loop that representing the potential there. So in many cases, this throws away important information about the problem. Yes, it's true. So despite what you may think in relation to the global warming, computers are incredibly efficient at arithmetic. Okay, we can make use of this. So this is an example of state-of-the-art of computational method, and I'd like to give you a brief tour of what happens if you are still remaining in the Stone Age and try to calculate with a calculator. Calculator can only be used for Olympiad problem, but not for research. Okay, so if you think that you are an Olympiad problem, and I'll give you a problem consists of 10 to the power of 18 particles. So use a pen and calculator. So your calculation would be 5 seconds for one particular problem. And then the total number of calculation required was 10 to the power of 18. And so you multiply this, you have 5 times 10 to the power of 18 seconds. Okay, what does it mean? Think about the age of the universe, 13.7 billion years. This is less than that, right? So your calculation is longer than age of the universe. If you do that, you want to do that? No way. So I would need 10 times longer than the age of the universe to do this calculation by hands. Even an Olympiad, well, maybe he can take 3 seconds to finish one particular equation. I don't think so, but then still you have a very long time. So then you need a computer, right, for that, instead of pen and paper. But please respect those who use pen and paper, right, because they are also brilliant. And if we can write 20 calculations per sheet of paper, so you need 6 times 10 to the power of 14 workbooks. That will be a stack of paper that reach from sun, starting from sun to Pluto. So I think that's not a good idea to have this lot of paper. But what about the ink that you use? You need a pen needs an ink, right? Or maybe a pencil. You need a carbon for that. Let's say I use 1 pen per workbook. Oh, yeah. Okay. Yes. So this worked out 6 times 10 to the power of 10 liters, which is 5 times volume of the outer Halifax Harbor, or maybe Tanjung Priok Harbor. Okay. So don't think about using this with a pen. So computer must be really energy efficient for this. But really, because computer use electricity. So for those who against computer wastes the energy. Okay. Let's think about this. Energy is measured in joules. 1 joule is 60 watt bulb. Each mathematical operation requires 2 times 10 to the power of minus 8 joule. Believe me, okay, really small. So even if you run that, okay, you're not wasting so much electric power for doing that per month. So this is a very good report to Buhesti, the head of the study program, because most of the students are using our server there. So you can calculate how much energy actually you use in this campus for that. But we are only one study program here, right? So only 0.5% of the average university's power consumption, Buhesti. So please let the student use the computer. Well, that's so. So maybe if you think about using your air conditioner in your house, in your room, so you are using 3 times 10 to the power of 9 joule in your house every month. So computer is good, right? Please love computer for your work. That's the idea. So let me have a short break here by having this short conversation with you. Who has worked extensively with Unix or Linux? Raise your hand. And also on Zoom, who are familiar with Linux? Okay, many. Good. We have Subam. Don't be shy, please. Yes, Linux. None of this room using Linux? Yes, not you, Pak Chandra. The students. So you're going to use that. So who has worked with some symbolic programming language like Maple, Mathematica, or MathCAD before? None? So, do you have any idea what language are very popular now for computer programming? Python. But have you heard about R? Yes? Why don't you mention R? Because R is not as popular as Python, right? Or do you think R is not a programming language? Actually, R is a synthesis of C, Fortran, and other, right, Buluki? You know that. So that's why R is actually a contribution from those Fortran programmer, C programmer, and Python programmer, Java programmer. So it is very much, well, there's a strong campaign in the United States of using R, but not here. I'm not an R user, so I'm not an R lover, but I'm an old-fashioned Fortran programmer, so don't worry about that. So it's good that a lot of you knows. May I assume that all of you, most of you knows Linux very well, because in many cases Linux is more advantageous for doing research, because it's basically a free platform. So you can start to learn that. Okay. Any question or maybe something? So can I maybe stop for maybe some question or expression or something? I know I start early in the morning, so to warm you up, let me invite you by some question if you like to ask. Or still sleepy maybe? Please ask question if you like. Yes. Yeah. I may say yes, but the way you do it doesn't have to comply on that. But in order to, of course, shape the research in a good way, because eventually what are you going to do when you do the research? You write a paper. So this paper must at least reflect your activity in that 6th stage. Well, yeah, some problems can be solved with a very well-known mathematical model. In that case, you don't have to describe the mathematical model. But perhaps you find some invention to discretize mathematical model into a very discrete way to make the computer works efficiently. That is one originality of you. You have to, of course, you have to say it out. So, but basically, that's a guideline from most of the papers. If you read about computer simulation or computer modeling. So when you come into that part, you have to, of course, obey this. Yeah. So sometimes it's important, first, is to help you plan computer experiments. Or second, you wrap up everything neatly and report it when you write a report, a thesis, or publication. So that's, you can consider this as a guideline. But for most of the computer experimentalists, they always consider this as a very good guideline to work it step by step. Okay? Yeah. And the first and the last is the hardest one. Because to make a computer run is very easy. Okay? But then to find a physical problem that you like to solve and to interpret your running is very hard. That is the way where you have to incorporate your knowledge about astronomy, physics, and everything to one coherent picture about the result of your computer experiment. It's a good question. Yes. Can I go through my time? It's only 1.5 hours. Still have a lot of slides. I think I put my slide here. But Iqbal, you have to like to say something? No? Yeah. Because when I look, you stand up. I think you like to say something. Yeah. So thoughts about computer technique. Programming isn't that difficult once you learn to think in a structured fashion. So this is a very good point. So actually, computer programming train us to think in a structured fashion. I'm not a computer specialist, I'm an astronomer, but I use computer to solve my problem. Okay, and the best way is to, shape my thought to be in a structured fashion. And for me, programming is very much helpful. Okay? So maybe for some of you, that is also apply. So, and I found that programming is not difficult. We have to try. Okay, I come to that slide. If you have a very free-form approach to problem solving, you might find programming is hard. Free means that you sometimes jump into this and that. Okay, so you have to shape this into one structured way of thinking. And programming helps you very much because programming works based on algorithm, the step-by-step. So my advice to learn the plan, how to plan this. Plan your thesis, plan your research. That's the best. Okay. So most numerical methods are comparatively straightforward to learn. Think about a numerical method. You learn only about arithmetic there, right? There is no complicated function when you learn numerical mathematics. Unlike mathematical methods in astronomy, you learn many transcendent functions, many difficult functions. But once you come into the lecture of numerical method, you only learn how to ask the computer to do arithmetic and the recipe for doing that. But nothing more than add, multiply, division, and of course, taking the negative or subtract. Okay. So of course, there are some exceptions in complex algorithm, but most of the time in astronomy we won't use that actually. In my experience, mostly instrumentalists, they use complicated, complex algorithm like Bessel function to actually model the point spread function of the aperture synthesis system. So that's the most difficult thing. But for a real physical problem in astronomy, we use a very simple, straightforward numerical method. You can get a long way relying on algorithm, but to be an effective researcher, you must understand what is going on. Okay. So I think this is a very good advice, not to rely so much on the black box, not so much rely on the ready-made software, and then we run the program there without knowing what is happening inside there. I think that's a very good principle when we use that. So algorithms are method for understanding the underlying physical problem, and don't lose sight of the fact that we are doing astrophysics. We are doing physics. You are a student of astronomy, not a computer. Okay? So bring it back to your mind. That is very imperative for you. So programming is the best learned by practice rather than watching. Okay? You cannot be a good programmer if you just watch people doing programmer. So this Confucianism principle is very good. You hear, you forget. You see, and you learn. But if you do it, you understand. It's a very simple way, invented by Confucius back in 551 before Christ. So programming is best learned by practice rather than watching. So think about, can you be a very famous concert pianist just by watching the performance? No, you have to do that. Okay? There is no substitute for doing the work and gaining the experience you need. And it isn't that hard. It's a formal process. It's hard to start, but once you start, you become in love with programming. When I was a very active programmer Even I dream about programming when I sleep. Think about algorithm, because some problem remain in my head and I fall asleep. And that sleep, I dream about that. And then when I wake, but unfortunately that dream didn't help me so much. It's just showing how desperate I am on that time. And these are about the common language. Surprisingly, Python is not the most one, starting from the survey in 2015 by Coding Dojo. SQL, Java, JavaScript still, yes, on the top position, but mostly because of programmers are making system program or web program. They are not making a scientific program, but scientific program is mostly occupied by C and Python or C++. And I'm so sad because no Fortran is here, because the age is of the Fortran is maybe somewhere there about this. So Python is a very good start for you to learn, and this reflects there are many users. The most efficient way to master a program is using the program that is used by wide audience and join the discussion group. Because you cannot finish, actually the textbook of Python is as thick as this. You cannot spend your time to read all of that. Okay? If you go to Japan, the book of Python comes in 4 and 5 volumes. So then come into the mailing list group or discussion group that will enrich you with many cookbooks actually about Python published that you can easily. I think young people is much more faster than me in grasping this. But keep in mind that SQL, Java, JavaScript is one of three top common language that it use. But unfortunately, I don't think Java is a very good selection for solving a scientific problem. I hope you agree with me. So, and also there is a driver for big data analysis in astronomy. Recently, people talk about data science, not computational science. So for some of them, they view this as a complement each other. But of course, computer scientists or computational scientists, they always think that they are not data scientists. But think about the data produced by optical astronomy, like large-scale synoptic telescope or radio square kilometer. Yes, radio square kilometer array. The problem is they create an avalanche of data. So 2 Sloan survey each day will actually flow you with so many data that anytime you can retrieve it for your work. And not mentioning about the radio square kilometer array is starting to be, and we have the James Webb Space Telescope now. And when the session comes, you will learn how actually people plan to produce data so fast with James Webb Space Telescope. So that actually going to be your, of course, area of research, your material to do research. So don't worry, in astronomy there's plenty of data. The number of stars in the universe exceeding the number of all astronomers in the world. So there are many stars that yet unlearned by us. Okay, but there are problems also. This is talking about the big data, but we also have this problem with the small data analysis too. For example, claim of detection of extrasolar planet. Even, well, when I spoke about astronomy research in the world, there are particularly 2 big groups. One focusing in survey, producing a large number of data. And one group try to work in a high resolution. I mean, high physical resolution, high time resolution, high spatial resolution. They like to investigate deeply in one particular object. This group mostly dealing with small number of data, but high quality data. While the survey people, they're mostly working on the large sample of data. And mostly the data signal to noise is not really high. But the key is to detect something new. So people like in the United States, when they use the James Webb Telescope, Large Synoptic Space Telescope, they tend to actually go to the frontier to find what is the farthest galaxy, yes, what is the farthest quasar that can be detected by this. But there are groups also in the world that are mostly dealing with small data, like people who try to investigate the atmospheric existence in the extrasolar planet. When we speak about extrasolar planet, it's very interesting. A large of group like Ogle survey, they try to, of course, detect and discover extrasolar planet. That's one important science. But but the other group are mostly concentrating a small number of this big number of extrasolar and try to investigate deeply. to answer, for example, fundamental question: does this extrasolar planet has an atmosphere? Okay. Does this extrasolar planet in the habitable zone may exhibit organic features in the spectra? So that also have some problems, because, for example, claiming detection of extrasolar planet have been shown to be inaccurate. So they address this by using a sophisticated statistical method or probability method based on Bayesian or frequencies to discuss and make sure that actually the extrasolar planet is not a brown dwarf or free floating object in the universe. So, and this requires new analysis paradigms, even with a small number of data. And this is because of pressure to publish means that senior researchers often don't spend time learning new tools. So the basic result of dealing with small data analysis is making a new method. So proposing a new method, new statistical, and this is the basic of why people now embark to the machine learning, for example, convolutional neural network, something like that. They are dealing with not so much data, but of course it's applicable for a large number of data. But basically, they develop this efficient way to for example, decrease the false alarm probability and increase the confidence level statistically to ensure us that we are dealing with the right sample depth. So these two areas is very interesting to see. Many papers published is basically on this two paradigm in solving a problem in astronomy. And speaking about Python versus R, I'm not promoting this because I'm not a user of this, okay? But I mentioned that many people here are using Python. I think our department of astronomy is actually most students are working with Python. They're so proud with Python. But think about these two. Why I compare this? Because R represents the symbolic programming language, while Python is procedural programming language. So when you think about Python, you think about Fortran, Basic, C. But if you think about R, you may try to find that similarity with Maple, Mathematica, and the other. So which one is better? Both are good, in my opinion. Okay? It's not fair to make, it's not an apple-to-apple comparison. This. Python is a general purpose, while R is a specialist one. So they're very similar in age. R is slightly younger. So when we talk about data science discussion, R has a stronger feature, while Python has more flexibility, because R was built with so many built-in packages that can be used. So many fields, R's visualization tools are more powerful than Python. You may disagree with me. Let's debate on this by using this best. R has a steeper learning curve. When you learn R, if you are good in learning Python, you maybe spend 1/4 only to learn and master R. So, well, speaking about preference, many Python programmers also use R to help them visualizing the result of that. So that's just a taste, okay? Okay, so let me go to the next. I'll give you a very brief illustration in modeling and computation, in particular in simulation astrophysics. But if you have any question from here, because I'm going to physics mostly after this. This gives you only a brief overview about the current state of computer and what is actually state of mind when we use computer to solve a problem that you have to go through. But if there's no question or anything else, Chandra, can you check maybe from the chat room any question? Nothing, only announcement. Yeah. From the floor, maybe you would like to ask anything. Please don't hesitate to ask anything. Yeah, Pak, please. Oh, you have to go. You can shout, Pak. Oh yeah, you are moderator. Sorry, you are.
Everybody can hear.
Yeah.
Yeah. My question is, 10 years ago, when we are doing programming using Fortran or C, there's one book, very good series of book, numerical recipes.
Yeah, numerical recipe.
There are many codes if you want to do like integration or generating random number. You can use some code in the book.
Yeah.
But now in Python, you already have some packages, so you don't have to do. Usually in the numerical recipe, you have to add in your code and how to interpret it.
Yes.
And now in Python, you already have many packages and it's so very simple.
That's right.
And the problem is now, so many students don't think again about the computation. They just put some how do you suggest for so
Well, that's better than using a black box. Because the purpose of people creating library is actually first, when I tried to flashback, it was happened in 1990 during my PhD in Japan. There were so many library published, and then we are discussing why this library published. That comes from the criticism of the people of so many programs created by astronomers and published. So how we can standardize this? So the best way is not to, of course, claim that program is bad or this program is good, but create the library. So to fill the library, the program must be benchmarked. Okay? Once it is benchmarked, it put on the library with a very detailed documentation, detailed caveats, detailed restriction that must be described clearly. So that library actually help us to speed up our research. And I used that heavily in my model at that time. So when I was a PhD student, I have to model a reflection. I have to make a reflection model of two binary stars. In it, one is the main sequence and the other one is subdwarf, 100,000 Kelvin. And this one is only 3,000 or 4,000 Kelvin, the surface temperature. And then what happened to this star? Because it's a closed binary, the period is only 1.2 days. So this hot star illuminates the main sequence. So that creates the heated hemisphere of this star. Then because of the star is moving in phase and out phase from us, it creates a sinusoidal. And if even the light curve is easy to solve that, it includes a very sophisticated stellar atmospheric problem. Because first you need to model the realistic temperature distribution of that star. And think about this star. This hemisphere temperature is about 30,000. When you observe, you see O-type star. But the averted is only 3,700, a G or K-type star. Okay? So these two different spectra comes from the observation. How to interpret this? How actually the meridional circle comes from this heated flow to the... So you need to make a hydrodynamic simulation for that. And you need a very realistic temperature distribution. So if I create the program for that, I have to write maybe 30,000 lines of program. So what I did is I used the library from the benchmark. And the most famous library is produced by Stellar Atmospheric Code made by Ron Crooks on that time. So that's the best one. So that is the age when library is very, very famous. So what I need to do is to make a main program, okay, arrange the flow of work, and then call this library, and then restore the program. That is also not easy, because what the library do is a very general thing, while your requirement is very specific. Okay? But that helps very much Python at that time. So that is how astronomer, scientists use library to solve the problem. So those who are in the library are very well benchmarked and very well guaranteed at that time and can be used. And it's not the black box, because we see the code. We can modify it. And there is, of course, a caveat that if you modify it, you have your own risk. the consequence will be you will provide that. And what we actually retrieve from the repository is the list of program, not the executable one. So we have to compile. So I think that's very good practice on that time. But to be honest, I don't know now. Because there is, I don't know about the situation now, but of course the library is still in the repository. You can, of course, subtract, or you can retrieve that anytime you like. But I think it's not a common practice now, I found. Because even if when I visited Thai, for example, there's the computer center, they tend to keep their own library rather than go to the LINPACK or StatLib. There's a very famous place. StatLib is library for statistical routine. And the second reason is because most of the library was created using Fortran. So that's why don't hate Fortran. Fortran still exists until the end of the universe, I believe. because when you come to the supercomputer simulation and you look at this program, so most of the parts are still written in Fortran. Because Fortran was the first programming language used by scientists. So the whole science idea actually packed into that beautiful code of Fortran. Okay. I say it beautiful because I'm a Fortran user. You may not say that beautiful, but it's beautiful for me. Yes. So that's the answer maybe by Iqbal for that. So I encourage young people, please look at the library. Yeah, and we have a Python library. Python library is much better maintained compared to the Fortran library. The reason is because most of the Fortran programmers are perished, so no one maintained that program, and young people doesn't like so much Fortran. So I hope it will not evaporate in the future. So you have to sometimes conserve the senior people to keep the Fortran alive for you. Yep, Iqbal, thanks for the question. And anyone else before I go through this? So let's now make a brief tour about how to develop our mind to do this computer experiment. Let me start from this. How can I do that? Yeah. So first, of course, we know from the very basic. I'm not going to this slide so long, but let me interest. What is remaining time, Pak Iqbal, for me? How many minutes do you have? 20 minutes. Yeah, I go through this, but this comes from our understanding about gravitational force. Okay, and Newton's universal law of gravity for the force between two bodies is given by this. I don't have to mention about this. But let us develop from our understanding about interaction of two bodies, action and reaction, into more, number of particles. Because gravity actually governs the force between two particles. So for example, if you put more than two particles, you have to first consider the gravity itself to one particular particle and the influence by the other particles. So you come into the problem where you have to extend this simple gravity force into several terms like this. This is only for an ensemble with 5 masses in our solar system. The more you go, the larger or longer equation that you need to write. But basically, it's a linear equation, right? With the same one. So the problem is not on the complicated or complex form of the function, but how do we actually arrange the force between particles and to the particle itself in this ensemble, in this arrangement. Okay? This is somewhat random, but in the case of solar system, we have a more regular arrangement of that because of the distance to the sun. So we need to calculate force on particle 2, 3 due to the other particle, and force on particle 5 due to all particles. So you can see that things getting quite complicated very quickly, and the computer could be of use on this, right? Because you know very well the equation. You can solve it analytically, but you have limited energy to do this, okay? Even for 5. Then that is the time when you ask computer, please do it for me. But don't be my master. You are the master of the computer for doing this. So how do you do that? You learn calculus. You can write down this in a more efficient way with the sigma and try to arrange this in a very careful way. So the interaction between particle and the other particle. Think about physical law that particle cannot interact with itself. So there's no mi square, but mi and mj for that. So you can see mathematical model for gravitational force is quite easy to discretize for our n particle. There are a couple of slight complications anyway for this because of that arrangement. Okay, so force is actually a factor of quantity, not a scalar. Up to that point, we spoke about force as a scalar, but when we introduce force as the factor, that means it has magnitude and direction. Okay. So our question doesn't tell us about the direction. And second, as the particle get closer together, the force is getting larger. In fact, particle I and j approach, then the denominator is going to 0. Right? Then you have a singularity in mathematical model for this. And if even in an analytical way it's getting singularity, what happens if you force the computer to do this? There will be an overflow. Smoke come out from the computer. Yes. Because of calculating 1/0. Believe me, that is a lie. Never have such happen. But of course, you have to overcome this by introducing a softened parameter. To put a small number here to prevent computer having 1/0 arithmetic. Okay? So that comes not from the computer, comes from us. Because we have the intelligence, not the computer have the intelligence for doing that. Okay? So that means that the remaining Rij give the direction of the force. So if we imagine that the position in 2-dimensional, then actually Rij give the force of its direction. So one trick in the computer discretization of mathematics is the softening parameter. This is a sort of softening parameter used by n-body simulation. There are many other kind of softening parameter that must be introduced, that has to be introduced to overcome computer facing this singularity that might happen when, as a consequence of discretizing continuous mathematical model for that. So this must be carefully chosen. If it is too large, it will affect the physics. You lose the accuracy because of this. But if it is too small, it will, of course, force the computer to do something beyond its capacity. Of course, you can put 10 to the power of -18, but think about 1/10 to the power of -18 become a very big number. Have you declared the variable to accommodate this as big as 1/10 to the power of -18? If you accidentally declare the variable as a single precision variable, it cannot accommodate 1/10 to the power of -18. Then there will be another error happen. Then this error will propagate. And once it's propagate through various steps, that become a brain damage for you. Because then you see the final result. What is this? A garbage in and garbage out. So you should prevent that to happen. So from the list of astrophysical example of an n-body system, you should be able to start seeing how each object can act as a single particle. Okay? In case of solar system, we need the sun and the 9 planets. And to be more accurate, you could include satellite, say N80. And what about the asteroids? We might want 1,000 of them in the asteroid belt. So now we have 1,080. 100,080. So you can see the number of bodies, even in our solar system, can rapidly increase when you go further from the sun. So even if you imagine only 5 mass, you see a long equation. Then you come to the 100,080. Okay, so if you want to model a small cluster of stars, you might want to use few hundred or thousand of stars. That's the area of Pak Iqbal, because Pak Iqbal dealing with a million stars, right, Pak, in globular cluster. You will need a few 100,000 particles. This means that the force on each star depends on the position and mass of other 100,000 stars in the cluster. You can see that a lot of calculating needs to be done. In fact, there will be n times n-1 calculation, or pronounce this, or this is order n square calculation that you must be done. Of course, not you, but the computer have to do. But think about the energy used by the computer, the memory will be used, the processing time and everything. And if you use the big computer by yourself, I don't mind. But if you use a server, many other students would like also to use. You have to be tolerant to them. Sometimes, however, you just cannot use a particle for every object in your system. You will not be able to use 100 million particles to represent all stars in the galaxy. So sometimes your particle actually represents a collection of physical bodies. So it's hierarchical. A cluster of stars becomes a particle when you consider a group of galaxy, because a galaxy. And a cluster of galaxy become a particle when you consider one part of the universe. So this is going hierarchical. But particle is very essential in this case. And I'm not going to the equation of motion, but of course equation motion is actually describing how the evolution of system is governed by. And this will tell us how system evolves with times. And there are two, for example, parameters important here, the velocity itself and the acceleration. Okay? Where acceleration depends on the position, velocity, and time. So acceleration is actually a wrap-up parameter that describing all the parameters concerning the equation of motion. I'm not going through this, you can read this, but the basic thing that you have to do is incorporating this into the first idea of mathematical model about position star. So this is the way we represent the physical model, the very first step. And next is, of course, transforming this into the discrete system and create a program and run it. And what happens when you do it? You come to the discussion or to the topic about accuracy and stability. Because once you make a computer experiment, you come out with the result. So the basic question is, does my calculation accurate? Does my computer algorithm work stable? This cannot be experienced when you use a black box. But if you use a program, you can trace this. Okay? So there are two more things that need to be careful of the choice of interval of time in case of dynamic, or interval of space if you use a static system. Okay? And number. These two cannot be reconciled. There is no good. The best is to find the optimum okay, selection of delta t, because when you reduce the delta t, the n is getting bigger, right? But then you have another problem. When you reduce the number of n, delta t is getting bigger. So you have to optimize. This is the word where optimize comes. Okay? You have to optimize this. So the time step controls the stability, and n gives the resolution of this. Of course, the best is to use a big computer that accommodates both of this, but we are not very luxurious in having that supercomputer. Okay? So that's why when you try to make a strategy of doing this, you think very carefully about having a very good combination of delta t and n for your simulation. Okay, so I'm not going to the n-body algorithm because time is not so much. How much time do you have? 7 minutes, okay? I think I have to go through this. These are some examples. I'm not going to this, but you can read it because I put it in the list. I go to the last part maybe just to facilitate. Okay, and once you have the computer experiments with some projects that I show you here, that will, of course, bring you a joy of running the model, okay? Then that is not the end. You have to improve the algorithm, okay? So improving the algorithm is mandatory actually for those who like to really solve the problem. But if you like only to exercise, you can just rely on the existing algorithm. But for those who are doing graduate study, you need to think about improving the algorithm. Because if you improve the algorithm, actually you introduce your genuinity, your novelty. Okay? So the best way when students always come to me and ask if I do this thesis work, can I claim some novelty in this? I answer with two. I make two answers. First, if you do observation, the data is your novelty. But if you do computer experiment, your program is your novelty. So even you make a very slight change in the very big source code, that's your novelty. You can build your program from the scratch or use the existing program and make some modification. That's better, rather than use a black box. Okay? So we can, yes, I'm not going to this, but let me, yes, put some idea. Of course, once you make an n-body simulation, that is not the end of the whole thing that you have to consider. Remember, in the universe, yes, universe is also mostly consists of gas and dust. And most of the observable comes from what is displayed, exhibited by the gas. Excitation, de-excitation, ionization, that comes from the gas. So that's why introducing gas actually in the simulated system is very imperative in astronomical simulation. Okay? Because we are not only dealing with particle. So this comes through this, but I'm not going to discuss about this because, for example, my group is doing photoionization modeling. Photoionization modeling is actually a gas modeling of the stellar system, a particular star system, in which you have to, of course, move from n-body problem into the problem of fluid. 6 here. Of course, some of the part will be addressed on this. So these are some of the examples that I'd like to show you, this around binary star. So to the end, this is the last part one. We have seen how computer experiments are a fantastic tool in modern astrophysics. Okay? And allowing you to understand the structure and dynamics of many systems in the universe, we have learned about how to set up n-body experiment and with some gas addition to give a clearer picture, a complete picture. And with the help of supercomputer, we can now increase the value of n into millions, allowing the universe to be studied in great detail. It is up to the computational astrophysicists, means you, to write better algorithm and codes to make use of this great computing power at your age now. Okay? And so when computational need is an astrophysics, I list here, I'm not going to describe this, just read. And if you are interested, please discuss with those who are expert in this field, starting from orbit of planet to formation of galaxy, and one independent topics is data analysis and image processing in astronomy. And yes, let me see here. And the future of the future of computational astrophysics, what is certain, increase in hardware will enable larger problem to be tackled numerically. Computer industry is still producing more efficient computer, and smaller and smaller and smaller. What is needed? More accurate algorithm. Community codes and visualization software, more realistic physics, and you, students, trained in computation. You are the real future. Thank you very much. Yes, please have a discussion session if you like. These are some of the credits. Pak Iqbal, I return it to you. Yes.
On YouTube.
Oh, YouTube, yeah.
Yes, one from Nimas. Hi, Dr. Hakim. I want to ask you, is there any program or software in astronomy using R?
Oh, yes. Oh, a problem. Yes, actually, I'd like to show you later. But I have actually a compilation of R. Mostly R is used for data analysis. Correct me if I'm wrong, Pak Buluki. But if you speak about simulation, also R has some problem. R has some library, actually, or repository in which you can solve simulation using R. Yeah. So the answer is yes, we have.
Okay, next question from Yoda. Are there any rule of thumb to set softening parameter other than trial and error?
No. It depends on how sensitive you see. So actually, yes, that's a very in computational, in the algorithm in the old time, we call it dummy parameter. And dummy parameter, there is quite a big liberty to use that, but that must be dictated on mathematical model that you use, okay, and the dimension. So that when we talk about the scale, this is a very different thing between physics and astronomy, because in astronomy we deal actually with the big number. Distance to the sun is 150 million kilometers. If I introduce a softening parameter, does it make sense if I take 1 centimeter or 1 kilometer? But if we use in physics, in finance, where the linear scale, the metric is not so big, so I think it makes sense if we have this. So it must be dictated by the physics, okay? And given the constraint that a computer cannot make a continuous, of course, calculation on that. So there is no rule actually, but it must be dictated by the physical concepts that we like and the range of number that we are dealing with. And astronomy is a big number, but biology, chemistry may deal with a very small number. So you have to deploy different softening parameter in each case.
Maybe one more question, short question from Subham, please.
Yes. Hi, Subham, please.
Hi, Professor. So you gave a very good talk. So thank you for that, first of all.
Thank you.
You in the last few minutes you talked about the photoionization modeling of gas clouds, right? So in that regard, so are you using some software packages for that, or you are doing some, like, you are developing your own code? Because I remember I have worked on my master's thesis research on photoionization modeling. So software
yeah.
called Cloudy. So are you using the same software, or like there are several other softwares or packages available?
When we talk about the flute, actually, I'm suggesting you to look at the hydrodynamic code,
Okay.
a fully hydrodynamic code. So there are some good code for hydrodynamics or software that you can use. Have you ever heard about FitDisk? FitDisk is a software to simulate binary interaction using smoothed particle hydrodynamics. And RFITs, for example, you can incorporate a flute model for doing a more realistic simulation. So, and the other is, of course, the best is to try to consult a good book like Numerical Methods in Astrophysics. This is a book which I use, and if you go to the chapter about the hydrodynamics here, that can be incorporated also in solving some of the binary problem, interacting binary problem. So I recommend you also to read this book. This is a very good book for the foundation, and have a look at the RFITs, FitDisk software, FitDisk. I will write it down to you. So I think you have a very good problem when you deal with the binary, because I'm familiar with that problem as well. Okay,
Yes,
stop
yes.
share here. Yeah.
No, what I was asking is for the photoionization modeling you were talking about, the
photoionization modeling, yes.
Yeah, gas cloud. So there is a software that I have worked is Cloudy. So are there any other packages or software to work on
I see.
photoionization modeling of gas
Yes,
cloud?
that's good. I like to share this experience. I'm still using Cloudy until now for photoionization model. But when I do the research on planetary nebula, for example, I approach it in two ways. One is to use the empirical one from the spectra, for example. We use the NIT, we call it NIT, to, of course, deduce the electron temperature and electron density. And this, with the spectral that I reduce, I use this as the input parameter to the photoionization code and produce a synthetic spectrum for that. So this photoionization, I think, is the best. Cloudy is still the best until now to be used for modeling photoionization of planetary. In particular, if you like to compare your observation with the synthetic spectra produced by photoionization model.
Yes.
So I think we share this similar tools, so sometimes we can discuss further about using the photoionization model.
Yes,
And
definitely.
yes, I'm glad to know you that because you are using photoionization. Not so much young people use photoionization model now for planet,
Yes,
not only for planetary nebula. Thank you.
Okay, thank you.
Great.
Thank you, Hakim. You give applause. Any question you can ask using our link. You already with your name. And okay, we will stop here and we will start again at 9:45. Okay, thank you very much.
Thank you.
Thank you, Hakim.
Yeah, thank you.
Students, don't forget to fill in the attendance form.